Assalamualaikum and salam sejahtera. So for today, let's continue our lecture by chapter 9. The topic is simple harmonic motion, and there are three subtopics there, which is 9.1 kinematics of simple harmonic motion, 9.2 graph of simple harmonic motion, and 9.3, which is period of simple harmonic motion. Okay, so let's start by the first subtopic, which is 9.1. So for 9.1, which is under kinematics of simple harmonic motion, from the learning outcomes, students should be able to explain what is simple harmonic motion and then solve problem related to simple harmonic motion displacement equation. Also derive an equation for velocity, acceleration, kinetic energy, and potential energy. Also emphasize the relationship between total simple harmonic motion energy and amplitude, and lastly apply velocity, acceleration, kinetic energy and potential energy for simple harmonic motion. So as usual, we need to start by the definition. What does it mean by oscillation? Alright, so according to this topic, the oscillation or periodic motion is defined as the back and forth motion of an object about a fixed point. Okay, what does it mean? See here, the object is moving again and again and again from one point to another point. Alright, and remember the displacement still remain constant here, means that there is no energy loss. Okay, so oscillation or periodic motion is the back and forth motion of an object about a fixed point, okay, between these two amplitude lah. Alright, so this is the simple harmonic motion. So basically, for the definition, what does it mean by the simple harmonic motion? So simple harmonic motion is defined as a periodic motion without loss of energy. Alright, again without loss of energy. That is why the object still maintain its position lah for the displacement. Alright, in which the acceleration of a body is directly proportional to its displacement from the equilibrium position or fixed point and is directed towards the equilibrium position but in opposite direction to of the displacement. Okay, so the keyword here is okay, repeated motion without any loss of energy. Alright, the acceleration now is directly proportional to the displacement but just in opposite direction of the displacement. Alright, so mathematically we may write down the equation to be like this. Okay, so the keyword now is acceleration. So acceleration now is directly proportional to the displacement. So y now representing the displacement. Alright, but opposite in direction. That is why we have to put a negative sign here to show that a and y, they are directly proportional but just in opposite direction. Okay, so according to the equation, okay, what do we have now? A is the acceleration of the body, omega now representing the angular velocity or angular frequency of the object which is moving now or oscillating now, and y, okay, this is y, it's not x, something is wrong here, let me correct this one first. Okay, this is y. This is y. Y now representing the displacement from the equilibrium position O. Alright, so don't be confused. As long the motion just be on x component, the displacement we take it as y. Okay, why? To avoid any confusion later, because we have two different displacement later. Okay, for the wave, right? In chapter 10. So x representing the wave propagation or distance, and y representing the displacement of the particle. Alright, so we just state y as the displacement from the equilibrium position O. Okay, so what do we have? Okay, what does it mean by this statement? Let me summarize for you using a simple diagram. Alright, so let's say there is a simple pendulum which is oscillating back and forth again and again. So this is a simple pendulum which is moving towards the amplitude, turn back to its original position which is equilibrium, and then moving towards another amplitude and again and again and again. So this is our periodic motion. So according to this situation, the object is moving from equilibrium towards the amplitude, turn back to equilibrium, and then moving towards another amplitude, then turn back to its original position or equilibrium, and this thing happen again and again and again. So this is what you call a periodic motion, okay, or simple harmonic motion. So in this case, according to the definition, A and Y, they are directly proportional, but it's just in opposite directions. Okay, what does it mean? So by assuming that the displacement is Y, so what happened now? Let's say this is the displacement, and starting from 0, the displacement just increase. Alright, so this is Y, which is increase. What happened to A? A also increased, but it just in opposite direction of Y. So based on that, our A just towards the equilibrium. This is A. Okay, so A, and A. As long Y increase, A also increase, but it just in opposite direction of displacement. Alright, so this is the definition of simple harmonic motion. So remember, and the keyword given now, acceleration, which is directly proportional to its displacement, but in opposite direction of the displacement, or this is the equation, the main equation of simple harmonic motion. So again, A representing the acceleration and Y representing the displacement from the equilibrium. Alright, and omega now representing the angular velocity or angular frequency. Okay, the example of simple harmonic motion system, 3 of it. Okay, the first one is simple pendulum oscillation, the second one is frictionless horizontal spring, and the third one is vertical spring oscillation. Okay, so how was it? Okay, we just refer to this diagram. The first one is simple pendulum oscillation, and the pendulum just oscillate again and again and again. Or frictionless horizontal spring, the spring just oscillating here, from the amplitude towards the equilibrium, and then reach another amplitude, turn back to equilibrium again and again and again. So the object just oscillating here. Or vertical spring. Okay, this is our origin. By pulling downward here, what happens? It will turn back to its original position or equilibrium, and then compress a little bit. That one is another amplitude. So turn back to the equilibrium, reach another amplitude. This thing happen again and again and again. So this is the example of simple harmonic motion system. Alright, you may refer to this video later. There are so many examples. You can see it clearly. Okay, how was it function? Alright. Okay, and then the equation here is A equals to negative omega squared Y, or dy squared over dt squared. Okay, means that by giving you an equation of displacement, we just differentiate it to time, and then you will get the acceleration. For the second differentiation, giving you acceleration. Alright. Okay, so based on this, as conclusion, A and Y, they are directly proportional, but it just in opposite direction. Okay, so the negative sign indicates that the direction of the acceleration A is always opposite to the direction of the displacement, which is Y. Right, and then how do we get the equation? Where does it come from? How do we get this equation? Okay, let me show you. Okay, so what happened now? When we pull the object outwards, by pulling the object outwards, there is a force acting on the object that tries to pull it inwards. So we are talking about the restoring force that is towards its equilibrium position. So by pulling the mass to the right, the restoring force just directed to the left, which is towards the equilibrium. Alright, when we push the object inwards, by push it inwards, okay, or by compressing the spring, what happened? The restoring force taught by the spring just directed outward or to the right against the compression. Okay, so towards its equilibrium position, again towards equilibrium position. In both cases now, there is a force, we call it as restoring force, acting on the block that tries to return the object to its equilibrium position. Restoring force causes the object attached to the spring move in simple harmonic motion. So what happened now? By pulling or push it, what happened? The object just moving again and again, repeated again and again and again. So we are talking about the oscillation. The object just oscillating here between amplitude to another amplitude through the equilibrium. Alright, so the force stored in the spring, now we call it as restoring force. This force is proportional to the displacement from equilibrium and always directed towards the equilibrium. Okay, so as we discussed before, by pulling to the right, the force just directed to the left or towards O. By push it to the left or by compress it to the left, what happened? The restoring force just directed to the right, still against O. So the restoring force always towards the equilibrium. Okay, according to the Hooke's law before. Alright, so by using the Hooke's law, what do we get now? Okay, so according to Hooke's law before, F equals to Kx, isn't it? But now the displacement, we take it as Y. Then the question is, F equals to negative Ky. What F is that? Restoring force. The symbol is Fs lah. So Fs equals to negative Ky. Alright, so Y is the displacement of the compression or elongation of the spring. So by applying Newton's second law to the motion of the block, as we know, F net equals to ma. And in this case, F net equals to Fs equals to negative Ky. So this is the second equation. From the first equation, F net equals to ma. From the second equation, F net equals to Fs or restoring force, which is negative Ky. F net equals to F net, so that ma equals to negative Ky. So based on this, negative Ky equals to ma, so that a equals to negative k over my. So from this, okay, we just compare with the general equation of simple harmonic motion before, which is a equals to negative omega squared y. So this is a and this is y, so that k over m now representing omega squared. Alright, so this is the hidden equation getting from this part, where omega squared equals to k over m. Okay, basically the general equation of simple harmonic motion given like this. Alright, so the main equation of simple harmonic motion equation for the displacement is y equals to a sine omega t. Okay, so basically this is the main equation of simple harmonic motion, which is under displacement. So y represented the displacement, a represented the amplitude or maximum displacement. Alright, omega is the angular frequency and t representing the time. Omega t, the values inside the bracket here, we call it as phase angle, which is the unit is radian. So normally, basically the unit of displacement is meter, amplitude also in meter. Okay, omega of course radian per second, time it must be in second. So radian per second times second giving you radian. The unit of phase angle just in radian. So basically by having this equation, how do we know? Sometimes the equation it can be in sign, sometimes it can be in negative sign, it can be in cos or maybe negative cos. So how do we know the equation should be in purely sign positive, purely sign negative, purely cos positive or purely cos negative? Alright, so we need to check the position of the object at t equals to 0. When t equals to 0, where is the object? Is it located at the equilibrium? Is it at the amplitude positive or is it at the amplitude negative? Because by having different position at t equal to 0, the equation also different. Okay, let me show you how to identify the equation. For example, at t0, the object at equilibrium position and then move to the right. Okay, so at t0, the object just located at the equilibrium, and then what happened? The object just move to the right, reach the amplitude, and then turn back to the equilibrium, and then reach the next amplitude, then turn back to its original position or equilibrium. So that the equation just in sine. So it must be purely sine and positive. How do we know that? Okay, it's quite simple. Let me show you. Okay, there is a pendulum system. So we just start from the equilibrium. Okay, so this is our equilibrium, this is our amplitude positive, and this is our amplitude which is negative. The object start from the equilibrium, isn't it? So for the first motion, the object just turn to the right and then reach the amplitude, turn back to the equilibrium, the second motion, and then from equilibrium reach the next amplitude, negative amplitude, that one is the third motion, and then it just turn back to its original position or origin or equilibrium. That one is the fourth one. So remember, in one complete oscillation, there must be 4 quarters. The first quarter, the second quarter, the third quarter, and the fourth quarter. So we are talking about one complete oscillation. Alright, so based on this, we just take out another graph here. Okay, so the graph of, okay, let's say y against time t. So in one complete oscillation, the time is period. Okay, so period at the middle here should be half period, and here should be quarter period, and here should be 3/4 period. Okay, so the object start from origin, isn't it? Or equilibrium. So the object start from here, and then it just reach the amplitude. Okay, one more thing, something is missing here. So this is the amplitude positive and amplitude negative. Okay, firstly, the object just located at the equilibrium, and then it just reached the amplitude after quarter period. It just reach the amplitude, then turn back to the equilibrium. Okay, for the next quarter, it just reach the negative amplitude, and then in one period, the pendulum bob just turn back to its equilibrium. So just be here. First motion, second motion, third motion, and the fourth motion. So from this graph, we know that the graph is purely sine, isn't it? So the equation is y equals to a sine omega t. So the graph is purely sine and positive according to this situation. Okay, alright. This is the first example given. For the second example, at t0, the object at equilibrium position and then move to the left. Move to the left first means that the object just reached the negative amplitude. Okay, how is it? Okay, we just take out the diagram again. Okay, so by having the axis, okay, so this is y against t. So amplitude, negative amplitude, and then this one is period, half period, quarter period, and 3/4 period. So remember, one complete oscillation must be equals to period. In one period, there are 4 quarters. Okay, first, the object start from equilibrium, isn't it? I'm using different color lah. I'm using the red one. Okay, so we just start by the equilibrium, and then just move to the left, reach the negative amplitude, and then turns back to its original position, which is equilibrium again, and then reach the amplitude positive, turn back to its original position. So first quarter, second quarter, third quarter, and fourth quarter. From this, we know that the graph is purely sine but negative, isn't it? So that y equals to negative a sine omega t. The question is purely sine but negative. Okay. For the third example, where is it? Okay, at t0, the object at positive amplitude and then move to the left. So the object start from the positive amplitude and moving to the left. How is it? Okay, so what happened now? We just draw the pendulum bob first. This is a pendulum bob. So we just start by the amplitude. So what do we have now? Amplitude, origin, and amplitude. Okay, amplitude negative, equilibrium, and positive amplitude. The object start from equilibrium. Amplitude positive, kan? So first motion. Sorry, I need to change the color. Okay, this is the first motion, and then second motion, third motion, and the fourth one. Alright, so according to the situation, what happened? Okay, so this is Y, and this is T. So this is period, half period, quarter period, and 3/4 period. So this is amplitude and negative amplitude. Alright, so the object start from positive amplitude, isn't it? Positive amplitude, here. So start from positive amplitude, and then towards the equilibrium, and then reach the negative amplitude, and then turn back to equilibrium, and then lastly back to its original position, which is positive amplitude. Okay, so first motion, second, third, and fourth. So according to the graph now, the graph is purely cos and positive, isn't it? So that the equation now is y equals to a cos omega t. Alright, so this is the way. How do we identify the equation? Just in purely sine or purely cos, and is it positive or negative? We just check the position of the object at t equals to 0. Alright, so there are so many examples. The next example given now, at t0, the object at negative amplitude and then move to the right. So the graph is purely cos negative. Alright, by doing the same thing, you will get this. Alright, so this is the equation of displacement for any simple harmonic motion system. Alright, how about the velocity equation? Okay, let's continue by the velocity equation. Okay, so for the velocity, the symbol is V. As we know, by having any displacement, okay, we just differentiate the displacement equation, then you will get V. So dy over dt now representing V. So y is the displacement. So by differentiating the displacement equation with respect to t, then you will get V. For example, y equals to a sine omega t. Okay, means that at t0, the object just located at the equilibrium and it just moved to the right, so that the graph is purely sine, isn't it? Based on this, we just substitute y into this equation, and then what do we get? Okay, this is the equation. V equal to dA sine omega t over dt. Alright, a just a constant. Okay, we just take out a to be like this. So V equals to a, and then d sine omega t over dt. So in this case, we need to differentiate sine omega t with respect to t, also omega t with respect to t. So by differentiating sine omega t, you will get cos omega t, and then by differentiating omega t with respect to t, you will get omega, giving you this, where V equals to a omega cos omega t. Alright, so this is the equation of velocity as a function of time in simple harmonic motion. Okay, don't be confused. Again, what do we have here? Let me show you again. Okay, so V equals to d over dt a sine omega t. Okay, in this case, we need to differentiate the first function, which is sine omega t with respect to t, and the second part is omega t with respect to t. Two different things, so that you will get a just a constant. Take out a sine omega t with respect to t, you will get cos omega t, and then omega t with respect to t, you will get omega. Okay, so omega and a just a constant, combined together, you will get a omega cos omega t. So this is the equation of velocity of any simple harmonic motion.